Okay, let's begin the semester by going over some preliminaries. This is part of your assigned reading. I hope you have had a chance to look at the first couple of sections, subsections in section 1 of the book. The main thing there is to get an idea of what is behind everything that we'll be doing, which is more of a discussion on how to think about the real numbers in a structured and rigorous way, more rigorous way at least than what you've learned in the past. So this will allow us to accomplish several things, not the least one being able to actually go over and revisit things from Calc 1 that were somewhat glossed over at the time for many of you. And in the process, we'll learn how to think mathematically in terms of structuring things, following definitions, the understanding and incorporation of certain concepts, and finally developing techniques for proving the theorems, and hopefully as the last step to be able to conjecture things that are real based on a correct mathematical intuition. Okay, so I just wanted to, well, I mean, so I said hopefully by now you've had the chance to look at the first couple of subsections in section 1. Section 1.1, you were confronted with the fact that something as natural as the length of the diagonal of a square may not make sense in the kind of numbers that you intuitively thought of as encompassing everything while you were in middle school. So square root 2 is not, I mean, if you want to define that number is not already included in the rational numbers. So you need to expand the notion of a number to include that very natural appearing number. And to discuss things related to the construction of the real numbers, I mean the numbers where square root 2 natural belongs to, we need to make sure that all the notation and all the basic logic needed background is there. So let's start with some fundamental concepts. So the first thing here is the concept of sets. Intuitively, and this is says in the book, a set is a collection of objects. I'm being very loose here. And the construction of consistent set theory is another topic that has led to the development of many good mathematics, but this is not the main thrust of this course. So we just assume that everything here is well defined. So it's a collection of objects, so we will understand it that way, and there's a correspondence with propositions also, because basically everything that we'll define for sets will be in terms of propositions being true. So notation wise, everything is important. So the notion of so we write that x is an A to mean that x belongs to A. We say that if A and B are sets, A is contained in B, and we write it in this way. In propositional logic, this means that this is equivalent to say that if x belongs to A, This implies that x belongs to B. Now, there are important operations that we'll carry out using sets. A union B is the union of elements in B and A. So in propositional logic, we say that X belongs to the union if and only if X belongs to A, or if X belongs to B. It may belong to both at the same time, but we just require that it's in at least one of them. Another notion that we need is the intersection. A intersect B. This corresponds to the elements that are in A and B at the same time. Again, there's a proposition associated to that, so the logic statement related to that is that X belongs to the intersection of two sets if it's in both of them. So X belongs to the intersection if and only if X belongs to A, and also X belongs to B. So X can fail to be an intersection if it's not in one of these two sets. It needs to be both at the same time. Now, the way we usually present sets. So we usually describe sets by means of a property or proposition that needs to be satisfied. The elements in the set. Okay, so one example that actually links what happened in the previous subsection is the set that defined in the book as the elements in Q, the set of rational numbers, such that r squared is less than 2. So far we only have the rational numbers. So we only know of the existence of integers and rational numbers. Okay, so we can write S as the set of elements such that r squared is less than 2. So you might think so. Well, one piece of a warning here. One may be tempted to say that this set is the same as R in Q such that R is less than the square root of 2. So what is the problem with that? I mean, of course, if R squared is less than 2, then R is less than the square root of 2 and vice versa. So these two propositions, remember this is an example of how we present sets. So we're describing a proposition here. Those are all the elements in Q are in Q such that what holds? R squared is less than 2. This is a proposition that may or may not be true. This is a property that defines the set. Okay, but you may think that these two propositions are the same, may be the same as asking R to be less than square root of 2. What's the problem here? Well, if you go back to the previous section, well, the problem is that so far we don't know the existence of a natural we can call the square root 2. So square root 2 is a property that is equivalent to the one above, provided what? Square root 2 exists. Since we only have the rational numbers and the square root 2 is not a rational number, we don't know the existence of such a number. So this property here cannot even be tested. Okay, so these sets, even though they might look like they are the same, I mean, they will be the same once we constructed the real numbers. But that's why we write this set in this way instead. So this set, here's just a piece of advice. Pay attention to these things. I mean, just don't assume whatever you learned before is going to hold. I mean, we're gonna the whole thing to a higher standard in this course. Okay, so this is very important. That's why people bother to write a set in this way. R belongs to Q if R squared is less than 2. Everything here is allowed and makes sense in the rational numbers. You can ask if the square of a rational number is less than 2. 2 is a number that is actually even an integer. And you can take the square of a rational number. All the things are allowed, so the set S is well defined, while the set down below is not up to this point. And how do we test? So going back to the property, how do we know or test if an element is in a given set? Well, we just check whether we check if the property defining the set is well, holds for that element. I'm not saying a number because sets can be made of more things than numbers. Sets can be made of sets, can be made of functions, and more complicated objects. It just so happens that in this case, the set S is made up of numbers in Q. Okay, so we need, in order to check if an element is in a given set, we actually have to look at the property and see if that element satisfies the property or not. And also, well, if you want to think about it in logic terms, you have to see if you plug in that particular element into the proposition, if that makes it true, the proposition true, then the element belongs to the set. So example, as an example, does 3/2 belong to S, the set as defined above? Well, let's check. We need to see, we need to check whether 3/2 squared is less than 2. Okay, so let's check that. 3/2 squared is the same as 3/4. And is that less than 2? So we put a question mark here. This can only be true if 9 is less than 4 times 2, which is 8. So, and this is not true, so this is false. So this is false. Okay, so 3/2 does not belong to the set S. What about 1.1? There's a tricky part of the proposition that we haven't checked here, and that's why I want to bring this to your attention. 1.1, well, you think, okay, we do the same thing and check whether 1.1 squared is less than 2. But there's something we're forgetting here. There are two requirements actually here. In the definition of the set S, R, the number, needs to belong to Q, and R squared needs to be less than 2. Naturally, for the first question, 3/2 is a number in Q. It is a fraction. But now what about 1.1? So because that's not written as a fraction, but we check that 1.1 is in Q and that 1.1 squared is less than 2. 1.1, so the first thing, so 1.1 is equal to 1 plus 1 over 10. Excuse me. So that's the same as 11 tenths, which belongs to Q. So this checks out. And the second statement is that 1.1 squared is less than 2. This is the same as 121 over 100. And this is just equal to 1.21, which is then less than 2. So again, so conclusion here. (1.1) belongs to the set S. Okay, so now this is a very gentle introduction to the kind of things we'll need to do from now on. We'll need to check everything that even if we're pretty sure that a statement is true, we need to check it rigorously. So everything that we claim, we need to prove, and we should try to get into the habit of doing so. We'll continue in the next video.